Ladies and gentlemen, good afternoon. I am Andrea Zanichelli, and I am a research fellow at the University of Parma in Italy. And first of all, I really would like to thank my co-authors from the same university. So, this research work deals with the simulation of an experimental campaign from the literature carried out on an aluminium copper alloy subjected to constant amplitude threatening fatigue loading by means of an analytical methodology recently proposed for the threatening fatigue assessment. Moreover, also the influence of some input parameters on both fatigue life and crack orientation is evaluated. So this presentation consists of the following sections. After a very brief introduction related to the threatening fatigue phenomenon, I will describe the analytical methodology employed. Then I will focus on the experimental campaign analyzed and on the results obtained by employing such a methodology. And finally, some conclusions will be drawn. So, very briefly, threatening fatigue. A couple metallic structural components subjected to vibrations or small oscillatory movements are prone to threatening, which can significantly affect their fatigue behavior. And in particular, microcracks may nucleate in the vicinity of the contact zone and correspondence of the high stress gradients arising especially in partial slip conditions. And then such microcracks can propagate in the presence of cyclic loading, thus leading to a premature fatigue failure of the component itself. Most failures due to threatening fatigue occur in a cycle fatigue regime and are characterized by high stress gradient and multi-axial stress state. So, in order to assess a threatening fatigue problem, firstly, the stress state within the structural component needs to be determined, and in order to do that, either analytical formulations or numerical models can be employed. Then, to perform the fatigue assessment, we need to apply a multi-axial fatigue criterion, and for example, a crack mutation model can be applied. And finally, the third remark is related to the high stress gradient. That is to say that, well, the stress parameters that have to be employed should be related not to a single material point, but instead to a sort of a process zone. And also the fatigue assessment should be performed at a certain distance of the contact surface. So we need to apply a non-local approach in conjunction with the above-mentioned multi-axial fatigue criteria. So now, let me describe the methodology employed that is quite similar to the one of the previous presentation. So the analytical methodology employed here allows us to estimate both crack nucleation direction and fatigue life for metallic structural components subjected to constant amplitude threatening fatigue loading in partial slip regime. The main steps are as follows. So firstly, the input napper needs to be set. Then the stress state is computed in the vicinity of the contact zone within the specimen. And as I already said, we can employ either analytical solutions or numerical models. Then the hotspot needs to be located on the contact surface. And then the orientation of the critical plane is determined by means of the joint application of the multi-axial fatigue criterion by Carpinteri and of the critical direction method by Araujo et al. And finally, the threatening fatigue assessment is performed at the verification point by means of the Carpinteri criteria. So let me go slightly into the details of this methodology. Firstly, three categories of input data needs to be set. That is geometric sizes, material properties, and loading conditions, as you can see here. Then the stress state needs to be determined in the vicinity of the contact zone. And so let us consider the typical threatening fatigue configuration shown here, in which we have two threatening paths, either cylindrical or spherical, that are pushed against the flat specimen in partial slip regime. This system is characterized by a plane strain condition, so it can be considered as a bidimensional problem. And so for this situation, analytical solutions are available, and accordingly, the stress tensor in the vicinity of the contact zone is computed by superimposing the stress components coming from the compressive load, the tangential load, and the cyclic axial load in the specimen. Then the hotspot is located on the contact surface by employing the equation reported at the top of the slide. That is to say that we assume that it is the point where the maximum value of the average maximum principal stress is obtained on the contact surface. And for the examined configuration, H, that is the hotspot, is found to be at the contact trailing edge. And this is in accordance with the fact that the main crack should nucleate in correspondence of stress concentration region. And as far as we consider experimental campaigns available in the literature, well, cracks always or generally have been found to nucleate at the contact trailing edge or very close to the contact trailing edge, just within the contact zone. So then the critical plane orientation is determined by exploiting the critical direction method in conjunction with the Carpinteri criterion. Very briefly, different material planes characterized by different orientation, that is the angle theta represented here. So it is the angle with respect to a vertical line, that is to say a line perpendicular to the contact surface, are examined. And for each of those material planes, we compute a fretting fatigue parameter, and according to this methodology, such a parameter is the equivalent stress amplitude and equivalent A, defined according to the Carpinteri criterion as reported here. Well, for bidimensional problems, each of those material plane coincides with a segment, as you can see here, starting from the hotspot on the contact surface, and then in length equal to twice d, where d is the average material grain size, in order to relate such a length to the material microstructure. Finally, the number of loading cycles to failure can be computed according to the Carpinteri criterion by solving the equation reported at the top of the slide, in which the stress components are those acting at the critical point and referred to the critical plane, where the critical point is assumed to be located, as you can see in this figure here, at the end of the segment equal to twice the average grain size of the material, starting at the hotspot on the contact surface and with an orientation given by theta critical, that is the crack nucleation orientation. So let me briefly describe the experimental campaign available in the literature and related to tests in partial slip regime on flat dog bone specimens made of aluminum copper alloy. In this table, the main material properties used in the methodology are shown. And as far as the microstructure, grains elongated in the longitudinal direction of the specimens have been observed during the experimental campaign, with an average grain size equal to 50 microns in the direction perpendicular to the surface. Then 4 groups of experimental tests with different fretting fatigue loading conditions are analyzed here, and those groups are listed in this table. For each group, cylindrical paths characterized by different values of the radius were used, and well, you can see here the fretting fatigue loading, that is contact load, and the amplitude, the ratio between the amplitude of the tangential load and the contact load, the normal load, and the amplitude of the bulk stress applied to the space. So let me now describe the experiment, the results obtained by employing this methodology. And in particular, on the left part of the slide, the calculated value of fatigue lives are plotted against the experimental ones. And as you can see, we have obtained quite a good estimation, since almost all the results fall within scatter band 2, and with an overall TRMS value equal to 1.66. On the other hand, on the right part, a broken specimen coming from the experimental campaign is shown. And 2 different zones of the crack can be identified. Firstly, we can see that the main crack nucleates and propagates for a few hundred microns with an angle that for the different experimental tests ranged between 18 to 32 degrees. And then the crack propagates to the inner part of the specimen almost perpendicular to the contact surface. So the analytical estimation of the crack nucleation orientation that we have obtained ranged between 6 and 11 degrees, and this value is related to double the grain size of the material, so a length equal to 100 degrees. And so those values should be compared with that coming from the experimental observation related to the first part, that is the one circled in red. So we can say that we quite underestimated the crack orientation. So let me now briefly discuss the main parameters affecting the fatigue life and the crack orientation computed by means of this methodology. These parameters can be narrowed down into 3 groups, that is contact geometry, fretting loading, and material properties. And in this slide, we can see the influence of the radius of the path on both fatigue life on the left and crack nucleation orientation on the right. Both those results decrease as the path radius increases when these results are computed by means of this of the present methodology. And in the figure on the left, the experimental estimations related to the group number 2 are also reported. And as you can see, also from an experimental point of view, of course, the fatigue life decreases by increasing the path radius. So relatively to the fretting loading, the different values and ratio, of course, of fretting loadings directly affect the stress state and accordingly the fatigue life. We can see some examples in the 3 graphs on the left part, where the fatigue life is plotted against the normal load, the amplitude of the cyclic tangential load, and the amplitude of the bulk stress. Whereas no significant effect on the crack nucleation orientation is found by applying the present methodology as a function of the fretting loads, except for the bulk stress, as you can see in the figure here on the right, where the crack nucleation orientation decreases if the amplitude of the bulk stress is increased. Then, relatively to the material properties, of course, fatigue properties are some of the most influencing factors in such a kind of problems, but in any case, in any other problems related to fatigue, so I don't want to stress this now, but I'd rather prefer to concentrate our attention on the coefficient of friction. And in this slide, we can see the influence of the coefficient of friction on the fatigue life computed by means of this methodology. In light green on the left, you can see the reference case, that is the results I showed some slides before, that are related to a coefficient of friction equal to 0.75, whereas on the right, we have the fatigue life computed by considering a friction coefficient of 0.5, and we have an increase of about 66% in terms of fatigue life. So we have less conservative estimations if we decrease the value of the friction coefficient, whereas the crack orientation is almost independent of the friction coefficient, since it only decreases of about 1 degree by changing the value. Then, in this slide, the influence of the average material grain size on the fatigue life is shown, and again, we have the reference case in light green on the left, and then we consider 2 different values of grain size, half and double the reference one. So in the case of a smaller grain size, the fatigue life decreases, and in the case of a bigger grain size, it increases, of course, because we are changing the sizes and the location of the point of the verification point. And as far as the crack orientation is considered, it can be said that it is slightly affected by the grain size change, since it decreases of about 2 degrees for the small grain size, and it increases of 2.5 degrees if the grain size is assumed equal to 100 microns. Finally, before moving to conclusions, I would like to consider an additional parameter, that is the relative microslip. In order to do that, we need to modify the assumption that the hotspot is located in the material surface only related to the stress state. So we can assume that the hotspot is the point characterized by the maximum value of the Ruiz parameter that takes into account both the stress state and the relative slip on the contact surface, as reported here. And also here we have in light green on the left the reference case, and on the right the estimations obtained in terms of fatigue life by considering the hotspot, maximizing the risk parameter at the contact surface. We can see that the fatigue life slightly decreased, only 4% of decrease, and the TRMS value is almost the same of the reference case, that is 1.64. And as far as the crack orientation is considered, it increases in this case of about 7 degrees with respect to the reference case. And so we obtained values of crack orientation ranging between 14 to 17 degrees. That is to say that they are values more similar to the experimental one, ranging between 18 and 32. So let us move to the conclusions. Experimental tests available in the literature carried out on an aluminum copper alloy in partial slip regime have been simulated by means of an analytical methodology that is based on the joint application of the Carpinteri multi-axial fatigue criterion and the critical direction method. Both crack nucleation orientation and fatigue life have been computed, and we have obtained satisfactory results in terms of fatigue life estimations with a TRMS value equal to 1.66. And whereas the results in terms of crack nucleation orientation quite underestimate the experimental ones. Then the input parameters related to contact geometry, threatening loading, and material property have been investigated, and they significantly affect the fatigue life, whereas they have at most a marginal effect on the crack nucleation orientation. And finally, the amplitude of the relative microslip has been taken into account, as obtaining fatigue lives very similar to those of the reference case, but with higher values of crack nucleation orientation compared to the reference case, and in this case, quite similar to the experimental one. Thank you for your kind attention.